In Lesson 3.1, we're going to be looking at relationships between lines and then ultimately angles formed from different types of lines. Let's start by looking at some line relationships. We know that two lines that never cross each other and are on the same plane, they are coplanar, are called parallel lines. So I can draw two lines and a line goes on forever in either direction. And when they're on the same plane, they're called parallel lines. I can have what's also called skew lines, and those are going to be two lines that are on different planes and don't intersect each other. So let's take a look at the example here. I have this line K and this line M. The way they're drawn here, they will never intersect each other, but they're not on the same plane, so they're not considered parallel. In this case, they're called skew lines. So I've got parallel lines, I've got skew lines, and then I also have the idea of parallel planes. Think of the ceiling and the floor in the room that you're in. When I look at the ceiling and the floor, they never cross each other, so they're parallel, and in that case, they would represent parallel planes. What I can do is take those concepts and then apply them to this box where I have a number of faces, and the face would represent a plane, and the edges which represent a line. So if I start with line CD here, I can find lines that are parallel to CD. So FE would be parallel, AB would be parallel, and GH would be parallel because I can draw a plane where both of those lines would be coplanar too. I can also find the lines that are skew. So if I start again with CD, I look at line AH. That never crosses CD, but it's on a different plane. The same thing with BG or FG. All of those lines never intersect CD, but they're on different planes from CD. They're not coplanar, so they would be considered skew lines. So what I can do is I can take this box figure and I can identify my parallel planes, my parallel lines, and my skew lines using that to represent the different figures. Moving into my first couple of postulates in this chapter, if I have a line and a point that is not on the line, there is exactly one line through that point that's parallel. I can draw lots of other lines through the point, but only one of those lines is going to be parallel. The same thing is true for a perpendicular line. I have my original line and my point. Only one line through that point will be perpendicular to my first line. Again, I can draw numerous other lines through the point, but only one line through that point will be parallel, and then one other line would be perpendicular to, in this case, line L. What I can do now is take a look at a situation where I have two lines. Now, these are not drawn as parallel lines, but then I have a third line that crosses them both, and it's called a transversal. Any two lines and a third line that crosses them, this third line is what is being called a transversal. What that allows me to do is come up with angle relationships between the lines and the transversal. So the first one I'm going to look at are corresponding angles. And a corresponding angle, they will live on the same side of the transversal and the same relative side of the two lines that the transversal crosses. So in this case, 2 and 6, they're both on the right side of the transversal, and they're both above their original line. So those two angles would be considered corresponding angles. When I think about my two lines in my transversal, I have lines that are going to be on the inside or the interior, and angles, I said lines, I meant angles, angles on the outside, which would be the exterior. So if I have two angles on the interior, they're inside or between my original lines. On opposite sides of the transversal, they're alternate interior angles. Same way, if I have two angles that are outside my original lines and on opposite sides of the transversal, I have alternate exterior angles. And the last category is when I have two angles that are inside my lines and on the same side of the transversal. In that case, they are considered consecutive interior angles. Now, these angle relationships will be critical to keep in mind, not just for Chapter 3, but throughout the rest of the geometry year that we have. So, corresponding angles, alternate interior angles, alternate exterior angles, and consecutive interior angles. So, when I draw this out, I can identify my relationships. So, let's take a look at Part B. What are my alternate interior angles? Well, interior is going to mean inside the two lines. Here's my transversal, so alternate will be 2 and 7, 4 and 5, alternating the sides of the transversal inside my original two lines. And so I can use my definitions from before to identify the names of each of these types of angles. Let's take a look at some of the examples here. Two lines, the angle is on the same side of those lines, the same side of the transversal. So in this case, I'm going to have two corresponding angles. For example, 4, here's my transversal. They're on opposite sides of the transversal, outside of my original lines. So I'm going to have alternate exterior. In this last case, on the inside of my two lines, alternate sides of the transversal. So these would be alternate interior angles. We can see how we use our two lines in our transversal to then define what we consider the angles to be. And in the next lesson, we're going to begin to see what some of the relationships are between those angles. Well, in lesson 3.1, we looked at having two lines and a transversal, and now we're going to look at a special case where we have two parallel lines with a transversal. Our angle relationships are still going to be the same. We're going to have corresponding angles, alternate interior, alternate exterior, and consecutive interior angles. The difference is when I know my two lines are parallel, I now have congruence understanding of the angles themselves. So in this case, two parallel lines and a transversal, I know that my corresponding angles are going to be equal. The angles will be congruent, their measurements will be equal. So in this example, where I have corresponding angles, angle 120 and the 120 degree angle and angle 5, I'm going to know that angle 5 is 120 degrees. I also know that angle 4 is 120 degrees because what we learned in chapter 1 was the idea of vertical angles. So all of these will be techniques that we apply to our drawing to figure out what our angle measurements are. So we started with corresponding angles. Let's continue on. We have alternate interior angles, alternate exterior angles, interior, exterior, and consecutive interior. So what I've learned now is corresponding angles are equal, alternate interior angles are equal, alternate exterior angles are equal, consecutive interior angles, this is a special case, those are going to be supplementary, which means when I add them up, they're going to equal 180 degrees. So it's really important to remember what the relationships are between the types of angles and their measurements when I have, again, two parallel lines and a transversal. when I look at this example, what I see is, to begin with, I can establish that the measure of angle 4 equals 115 degrees because those are vertical angles. I also know that line A and line B are parallel. That's what these little red arrows show me. And so now I can also establish an equation because I know 4 is 115, and those two are consecutive interior angles. And so I add them up, and I can solve for x. I have to consider using all of the different relationships that we've learned. Now, there are going to be oftentimes different ways to solve this problems, but pick the one that you recognize, that you see, and then methodically apply the various angle relationships that we've just talked about. Here's another example. I have two parallel lines and a transversal. So I know my corresponding angles will be equal. My alternate interior angles are equal. Remember, I have two sets of those as well. My alternate exterior angles, my consecutive interior angles are going to be supplementary. And so I have a lot of angle relationships here that I can apply in order to find the measurements of each one. In lesson 3.2, we looked at the relationship between angles when we knew that lines were parallel, two parallel lines and a transversal. Now what we're going to do is take the situation where we know angle measurements are equal in order to prove that lines are parallel. So for example, as we saw in lesson 3.1, 2 and 6 are always going to be corresponding angles. But in the special case when they are equal, by definition then, I know that these two lines are parallel. Because the angles are equal, I know the lines will be parallel. If the lines are parallel, I know the angles are equal. I can use either of those relationships to either solve for an angle or prove that lines are parallel. So in this example, what I want to do is I want to solve for x in order to know that the lines are parallel. Well, those are going to be corresponding angles, and so I can set up my equation to make them equal to each other for the special case when they're parallel, solve for x, and then when x is 20, I know that line M and line N are parallel because those two angles are going to be equal. So again, I can go from parallel lines to find the measurement of angles, or I can use the measurement of angles in order to prove that lines are parallel. In this case, I have a situation where I don't have a direct relationship between those angles. They're not corresponding, alternate interior or alternate exterior. However, I do know that these angles form a linear pair. It's another concept we learned in chapter 1. Because they form a linear pair, they're going to be supplementary, meaning they add up to 180 degrees. So since this is 105, I know that angle will be 75 degrees. And if this is 75 and that's 75, those are now corresponding angles. Since they're equal, I've just proved that those two lines are going to be parallel. As we continue on, the same thing is going to be true for any of my other angle relationships. If I have alternate interior angles and I know they're equal, lines are parallel. Alternate exterior angles, same thing. When they're equal, the lines are parallel. And the last is when I have consecutive interior angles. When they end up being supplementary, they're going to prove that my two lines that created them are going to be parallel. Supplementary, parallel, equal. In their relationships, those lines are going to be parallel as well. So I have a situation here, some examples. Let's see if we can figure out for sure whether we know these lines are going to be parallel. Well, in this case, I have alternate exterior angles. They're shown to be equal. I know the lines are parallel. In this case, I have corresponding angles. Again, they're shown to be equal, and so I know my lines are parallel. In this case, though, the angles are shown to be supplementary, but they're also alternate interior angles. So in general, this would not prove that those lines are parallel. However, could be the special case, if both of those angles are 90 degrees, then they're going to be equal and they're going to add up to 180 degrees. So there can be a special case, but again, in general, based upon what's drawn in example number 5, I cannot state that the lines are going to be parallel for sure. Last couple of things for this lesson. If I know two lines are parallel, and one of those lines is parallel to a third line, then I know all three of the lines are parallel. It's kind of like the age-old, if A equals B and B equals C, then A equals C. Well, if two lines are parallel and one of those is parallel to a third, then all three lines are parallel. Pretty straightforward and seems to be common sense. And what that will help me do then is going to help me identify angle relationships across multiple lines with transversals. In lesson 3.4, we're now moving to look at the specific aspects of a line as it relates to its slope. And most people will probably remember that the slope of a line is considered rise over run. The reason it's considered rise over run is because I've got my change in my y value, which is my rise, and my change in my x value, which is my run. And when I'm able to calculate that, I know what my slope is. You may also hear this at times called delta y, which is change in y, over delta x, change in x. That's how I calculate the slope. One of the things that's important to know is that the way the equation is set up, I have y2 minus y1 over x2 minus x1. In reality, it doesn't matter which ones I choose to be ones and which one I choose to be twos. I can make this the ones and this the twos, or I can make this the ones and this the twos. The key thing is to always be consistent by using the coordinates of a point for both x and y as either the 1 or the 2. And so now I have 4 different situations where a line has some type of slope. The first one is considered a negative slope. It's going downhill because I'm always looking from left to right. When the line goes downhill, it's going to be a negative slope. When a line goes uphill or rises, it's going to be a positive slope. If a line is horizontal, which means it's going to be parallel to the x-axis, the slope is actually 0. And when I have a vertical line, the slope is undefined. The reason for that is my change in x is 0. And if we remember, my rise, which is y's, over run, I now have something divided by 0, and I know that doesn't work, which is why a vertical line does not have any slope. It's undefined. So downhill negative, uphill positive, flat is a 0 slope, straight up and down is undefined. What I'm able to do now is use different coordinate points in order to determine the slope of a line. If I'm looking for the slope of line A, I've got 6, 4 is 1 point on the line, 8 and 2. I set up my change in x and my change in y. rise over run, and I find my slope is -1. Makes sense because I know this line is going downhill, so it should be a negative slope. Same thing is if I look at the slope of line D, I can show that it's undefined because there's no change in x. It's a vertical line, and so I cannot calculate the slope for line D. I can take any 2 points on a line, apply it into my change in y over change in x, rise over run, and I can come up with the slope of the line. If I have 2 lines and they're parallel, which means they're not going to intersect, they're going to have the same slope. Kind of makes sense. Whatever downhill amount this one has is the same as the downhill amount that one has. So parallel lines, the slopes are equal. A perpendicular line, where it creates a 90-degree angle with my original line, it has a slope such that when I multiply them together, the slope of the first line, and m represents slope, times the slope of the second line equals -1. I can also say this is the negative reciprocal. That's another easy way to think of what this equation means. So for example, if I have a slope of 2 for one of my lines, the perpendicular line is going to be -1/2. When I multiply those together, I get -1, and we can see this is the negative reciprocal. I went from 2 over 1 to 1 over 2. That was the reciprocal, and I made it negative. That's how I can identify the slope of a perpendicular line. One of the things that allows me to do is to calculate the slope of different lines to see, are they parallel? Are they perpendicular? In this case, I have 3 different lines, and I find that the slope of line 1 and 2 are the same, which means they're parallel. The slope of the third line is very close, but it's not exactly the same, so that line is not going to be parallel to the other two. Same thing will be true here for a perpendicular line. I can identify my original line and figure out the slope of that, and then I look at my rise over my run of the negative reciprocal, so that when I multiply them together, they end up being -1. And so I found the slope of my first line, I do the negative reciprocal, and then I can map out by going down 2 over 3, down 2 over 3. Change over y, change over x, and then this is my second perpendicular line, and that was my original line. So I can use my slopes to help me map out what I need in terms of the various lines. The last thing what I can do is I can determine the slope based upon information that's given. And I can see if something is rising faster than another line. So if something has a steeper climb, it's going to have a steeper slope. And in this case, what they're doing is they're measuring the difference between 2 different roller coasters to see which one is actually steeper. In lesson 3.4, we were looking at how to calculate the slope of a line, and we looked at the relationship between parallel lines and perpendicular lines. Now what we're going to do is we're actually going to come up with an equation that allows us to graph a line. The form that we use is called the slope-intercept form. And the slope-intercept form is y equals mx plus b. As we read here, m is the slope. So anything in front of the x, when the equation is written this way, tells me exactly what that slope is. And b is called the y-intercept. That's going to be where it crosses the y-axis. And so now I have a standard form to represent lines in an equation form. So the first thing I have to do is I always have to find the slope. That's going to be my first job. So I've got 2 points graphed here, and I'm looking for the equation of the line. The first thing I do is find the slope. So I found my slope, and that's going to be -2. My rise over my run, change in y's over change in x. The next thing I do is find where the line crosses the y-axis. Well, I already see that here because in my drawing, I can see it crosses the y-axis at 4. So I know b equals 4. Now, using this information, I can write an equation for every point on that line. Y equals mx plus b, which is, oops, I wrote b. What I meant to write was 4. Mx plus b. That's the equation of this line. And I'm able to do that by finding my slope, finding my y-intercept, where it crosses the y-axis, and then turning it into a standard form. Now, here's one of the cool things about the equation of a line. Any point that is actually on that line, when I plug it into the equation, it works. If I get 2 equals 2, that works. 5 equals 5, that works. If a point is not on the line, then I get an inequality. I might get 4 does not equal 3. Whatever point, when I plug into the line, gave me that, tells me that point was not on the line that I was working with. So every point on a line will solve the equation so that it works out correctly. Let's take an example here. So the first thing is we have the equation of a line that we're starting with. And now we're looking for a line that's parallel to that. Well, I start by finding my slope. When I look at this, mx, 2x, 2, the slope of my line that I'm given is 2. But since it's parallel, my new line, it's going to have the same slope. So I'm done with that part. The next thing I have to do is solve for b. Well, this one isn't graphed for me, so I'm going to have to take this point and my slope and create an equation where I solve for b. I simply start with y equals mx plus b. I know that -1, 1 is on the line, so I can plug this into my x and y. I can plug this into my m, and all I'm left with is my value for b. So when I do that, y equals 1 equals, my slope is 2, x is -1, plus b. 1 equals -2 plus b. I add 2 to both sides, and I end up with b equals 3. Find the slope, solve for b. Now I plug this and this back into a standard equation. Y equals mx plus b. That's the equation of a line parallel to this one that passes through the point -1, 1. That approach is something that I'm going to be using time and time again. Find the slope, solve for b, and then plug it into the standard equation. In this case, I want to find a line which is perpendicular to this equation going through that point? Well, my first line has a slope of -2. My new line is going to be perpendicular, which means it's the negative reciprocal, which is 1/2. Because when I multiply -2 times 1/2, I get -1. Negative reciprocal, that tells me the line is perpendicular. So, step 1, found the slope. Now I have to solve for b. I use my standard equation, except I just plug this in for my x and y to solve for b. So y equals 3 equals mx, which is 2, plus b. 3 equals, that goes to 1 plus b. When I subtract, I get b equals 2. Now I have my slope, I have my b. I can write my equation of the line that I'm looking for, which is going to be y equals m, which is 1/2, x plus b, which is 2. That's the equation of a perpendicular line to this one that passes through point 2, 3. Find the slope, solve for b, plug it in, and I get a standard equation. And again, every point on that line will then solve the equation correctly. Here's a situation where I want to find the equation of this line. I'm given some data. I'm given 2 points, so I can find my slope, step number 1. I can choose either of these 2 points because they're both on the line in order to solve for b, step number 2. And then I simply plug that in to my standard equation, y equals mx plus b. M is my slope, there's my b, and I get this equation. Didn't matter which of the 2 points I used to solve for b, I would get the same b because both of those are on the line. Again, every point on a line will solve the equation correctly. Here's a situation where I'm being asked to graph a line, but while this is in a standard form, it is not in slope-intercept form. So what I have to do ultimately is I can solve for x and y here because I'm simply looking for where it crosses. But if I wanted to get the equation of this line in slope-intercept form, I would have to ultimately solve so that it was in the format y equals mx plus b, which means I'm going to have to move my x over, get rid of my 4, and then I can turn it into this format. However, all I'm looking for here is the ability to graph the line, so I can plug in my x and my y's and solve in order to graph my line. The more interesting situation is where I want to turn it into an actual slope-intercept form equation. Okay, we're wrapping up Chapter 3 with Lesson 6, and now we're going to be looking specifically regarding theorems about perpendicular lines. So the first theorem says if I know 2 lines are perpendicular if these 2 angles are equal. The reason I know that to be true is that these form a linear pair, which means they add up to 180 degrees. If they're equal, they both have to be 90 degrees. If they're 90 degrees, they're right angles, which means the lines are perpendicular. I also know that if 2 lines are perpendicular, that all 4 of my angles are going to be right angles. Those are pretty straightforward concepts in terms of the first couple of theorems we're looking at. For this first example, if I know, because I'm told, this is my little perpendicular sign, that these 2 are perpendicular, I know angle 1 equals angle 2, and they're both right angles. It's pretty straightforward from what we just looked at. Now the other thing is, if I have a right angle that is split. So I've got two angles, remember our angle addition theorem, that make up a right angle. They're going to be complementary because angle 2 and angle 1, when I add them up, 2 and 1, they're going to add up to be 90 degrees, and we know that two angles that are complementary add up to be 90 degrees as well. Again, pretty straightforward. Here's an example. If I know that ABC, which is this angle, and ABD, which is this angle, if they're equal, I learned from the first theorem that they're going to be right angles. And if this is a right angle, then I know 3 and 4 will be complementary angles. I don't know what their measures are here, but I do know that they're going to be complementary. A couple of other theorems. So when I have two parallel lines, if I know these lines are parallel and I have a transversal that is perpendicular to one, I know by definition it's going to be perpendicular to the other. So a transversal perpendicular to one of two parallel lines is going to be perpendicular to both of them. Likewise, if I know I have a line, which would be considered a transversal, perpendicular to two other lines, these two lines by definition will be parallel. All I'm saying is that when I've got parallel lines and a transversal perpendicular to one, it's perpendicular to both. And if it's perpendicular to both, I simply know that the lines are going to be parallel. So if we take a quick look at this example, I've got two lines here and a transversal perpendicular to both. I know those two lines are going to be parallel. If I look at these two lines and this transversal perpendicular both, I know those two are going to be parallel. I can simply apply my understanding of the perpendicular lines and the transversal to prove that lines are parallel. One last thing is that if I'm looking at distance, so if I have a point not on a line, the distance to the line is going to be a perpendicular segment from the point to my other line. Same thing as if I have two parallel lines, the distance between them will be a perpendicular segment. It's perpendicular to both of the parallel lines. It's like a transversal. And every segment that is perpendicular to both will represent that same measurement.